Hi class, today we are going to learn about the fundamental counting principle, and I highlighted fun because it'll be a lot of fun. So in the previous lesson you learned about sample spaces and tree diagrams. And basically a sample space and a tree diagram, it tells you how many outcomes there are, how many total outcomes there are. Well, the fundamental counting principle tells you the total number of outcomes as well, but it's a much easier way of finding it. Rather than creating a sample space or a tree diagram, you actually just multiply the number of outcomes for each separate event. So I'm going to show you, for example, number 1 here, Carrie rolls 2 dice. So they're numbered 1 through 6, and I want to know how many outcomes are possible. So if I were to use the method that we used yesterday, I would write out 1 through 6. So on my first roll, I could get a 1, a 2, a 3, a 4, a 5, a 6. Well, then on my second roll, I can also get 1 through 6. So I made a tree diagram. So I could roll a 1 and then a 1, a 1 and then a 2, a 1 and then a 3, a 1 and then a 4, so on and so forth. Sorry guys, I know you probably hear my daughter cry. So if I were to count this, there's 6 outcomes here, 6, 6, 6, 6, 6. This took a lot of work, so I did it ahead of time. That means there are 36 total possible outcomes here. Well, another way of doing that is just to multiply. So the number of possible outcomes in my first roll, I have 6 possible outcomes in my first roll, and I have 6 in my second roll. So I just multiplied the 2 together. The number of possible outcomes in your first and the number of possible outcomes in your second, and you get 36 total possible outcomes. I know, you're probably hating me right now for making you learn how to use sample spaces and tree diagrams because they're definitely a lot more work. This is definitely easier, but I wanted you to understand where the number came from first, and now we can just apply the fundamental counting principle to all of these problems to make it easier. So we're going to just work through 6 problems together. Number 2. Sammy picks 3 1 through 5 number cubes from a bag. After she picks a number cube, she puts it back in the bag. How many possible outcomes are there? So Sammy picks 3 from a bag. Well, the first try, she has 1 through 5. So 1, 2, 3, 4, 5. There are 5 numbers there, so that's 5 possible outcomes. She puts it back in the bag and she picks another number cube. She has 5 possible answers that she could get there. 1, 2, 3, 4, 5. She puts it in the back in the bag and she selects it again. Okay. So if she picks 3 times, that's 5 times 5 times 5. She has a total of 125 possible outcomes. I would not want to create a tree diagram with 125 possible outcomes. That would be a very big tree diagram. So this is a lot easier to do. Now, it doesn't list all the outcomes, but I know that there are 125 possible outcomes. Number 3, a bag contains a red, a blue, and a yellow marble. Bag B contains a white, an orange, and a green. Frederica draws 1 ball from each bag. How many outcomes are there in the sample space? Okay, so in the first bag, bag A, there are 3 possible outcomes. And then in bag B, there are 3 possible outcomes, white, orange, and green. So we just multiply them, and that means there are 9 total possible outcomes. So I would have 9 answers in my sample space if I were to create this. Right, Sam tosses a coin and rolls a number cube. What are all the possible outcomes? Right, so I would first find the probability of her tossing a coin. Well, that's 2. There's 2 possible outcomes there. Then if I roll a number cube, a typical number cube has 6 numbers, 1 through 6. Okay, and then so that would give me, if I multiply those 2, it would give me the total possible outcomes. So 12 outcomes. And that makes sense, right? I could have a head and a 1, a head and a 2, a head and 3, head and 4, head and 5, head and 6. Then I could have a tail and 1, tail and 2, tail and 3, tail and 4, tail and 5, tail and 6. That's 12 outcomes, okay? All right, now we're going to move on to a little bit more challenging problems. So license plates are being produced that have single letter followed by 3 digits. All license plates are equally likely. So we're going to use the fundamental counting principle. Let me hide some of this. To find the number of possible license plates there are. This is really interesting. I want to know how many license plates there can be. Right, so it's always a letter first. Well, there are 26 letters, A through Z. Okay, so 26. The first digit, okay, so digits. We have 0 to 9, so there are 10 possible digits. The second digit, it doesn't say that it can't repeat. It actually says that they're all equally likely. So it could be like A222, right? That could be a license plate. So there are 10 digits there from 0 to 9. The third digit is 0 to 9 as well, so 10 digits. So these are all the possible outcomes in each one. So then from here, what I would do is I have to multiply all of them. So 26 times 10 times 10 times 10, okay? And that would give me 26,000. So there are 26,000 total license plate that have a letter followed by 3 numbers. That's a lot of license plates. That's so interesting. Okay, now I want to know the probability that the license plate has the letter Q. So it has to be Q, but then it can be any 3 numbers after that. So I'm going to kind of set it up the same way that I did up here. So 26. Now I don't have 26 possible letters to choose from. I only have one because I want it to be a Q. So there's one choice there. Well, the first digit, there are still 10 possible outcomes. The second, 10. The third, 10. So to find this, I have to multiply 1 times 10 for the first digit, 10 for the second, and 10 for the third. Therefore, I have 1,000. Now, I want to find the probability. So this is 1,000 out of the total amount of trials, remember? So the total number of possible outcomes, which is 26,000. So 1,000 divided by 26,000, that would simplify to 1/26 or 0.038. Now remember, this is the decimal form, so if I wanted to know the percent, I have to multiply that by 100, and I get 3.8%. All right. So get one more in this problem. It says find the probability that a license plate does not contain a 3. Okay, so I don't want the license plate to contain a 3. Okay, so I can have 26 letters. That doesn't matter. Okay, can't contain a 3. So normally there's 10 digits to choose from. Now I only have 9. So it can be 0, 1, 4, 5, 6, 7, 8, 9. Okay. Then I have 9 digits to choose from. And again, 9 digits to choose from. So 26 times 9 times 9 times 9. And then that's going to be all over the total number of possible outcomes, right? Probability out of the total 26,000. I'm going to pick up my calculator. 26 times 9 times 9 times 9 is 18,954. And I'm going to divide that by my total number of possible outcomes, 26,000. And you get 0.729. So that means that it's 72.9%. The probability of not having a 3 is 72.9%. That's pretty high to not have a 3 in your license plate number. Okay, we're going to do one more problem together. This one I find so interesting because everyone has a social security number. They're all 9 digits long, so all social security numbers are equally likely. So we're going to use the fundamental counting principle to find the number of possible security numbers. All right, so there are 9 digits, right? So let's draw lines. 1, 2, 3, 4, 5, 6, 7, 8. Running out of space here. Make that 9. All right. There are 9 spaces, okay? All right. Now, there are 10 possible digits for the first number. There are 10 possible digits for the second, 10 for the third, 10 for the fourth, 10. So each one of your numbers in your Social Security, there's 10 possible outcomes, okay? So that means to find out how many possible outcomes there are, I have to multiply all of them. 10, 9 times, right? That's just 10 to the power of 9. 5, 6, 7, 8, 9, 10. Well, hold on. 3, 4, 5, 6, 7, 8, 9. Okay, I didn't want this last one. There are only 9 numbers, okay? So we would multiply all of those together. Wow. That is a lot of Social Security numbers. That's insane. It's amazing. Next, we're going to find the probability that the Social Security number contains a 7. So there's at least one 7 in it, okay? So for the first number, what we're going to do is we're going to make the first number have to be a 7. So this one, we have to have at least one 7. So that means there's only one possible outcome for the first number. It is going to be a 7. Well, for the second number, it doesn't have to be a 7. It could be any 10 digits. So that means we need 8 10s because there are 8 other numbers in your Social Security that can be any number, including 7. It just says it needs to contain a 7, so that means one 7. One, 2, 3, 4, 5, 6, 7, 8. Wonderful. Okay. So you would multiply all of these together, but you have to divide by the total, right, to find probability. You multiply it by the total possible outcomes. All right. And when I do that, you get 1/10 or 0.1. So 0.1 is 10%. All right, so 10%, the probability of getting a Social Security number with at least one 7 is 10%. All right, find the probability that a Social Security number does not contain a 7. So that means there are 9 numbers and it can't have a 7. Therefore, instead of 9 possible outcomes, or 10, there's only 9. This number can only have 9 because it can't be a 7. 9, 9, 9, and there are 9 numbers in your Social Security number, so we need 9 nines, or 9 to the power of 9. 3, 4, 5, 6, 7, 8, 9. Perfect. But now remember, you always divide by the total possible outcomes there are. All right, so we would divide that, multiply all over 9, and then divide, and you would get 0.4. Now 0.4 is the decimal, so that's 40%. So the chance of not having a 7 in your Social Security number is 40% chance. All right, there is another video in the folder if you still need a little bit of extra help. Go ahead and watch that, and then you can go ahead and complete the Schoology assignments. I hope you guys are all doing well, staying safe and healthy. Have a good day.